Okay, so we're here in the only room that really has any natural light to speak of for a few little notes and clarifications from the last video, which you should definitely check out first up here. There wasn't really time in the last video to talk about performance, a couple terminology things, and this ridiculous shirt. So let's get into it. So there's definitely a good reason why languages have the default that they do, passing arrays and objects by reference and allowing mutations on them instead of being immutable by default. And definitely the main one is performance. Copying an array is not an efficient operation at all, so it does not really make sense for that to be the default when passing values into a function. First off, when you're copying an array, you have to find a place in memory to store all those values in one block. Just like finding a place for that weirdly shaped container of food in your nearly full fridge. And once you do find that space in the fridge or in memory, you then have to copy over every element from the array one by one by one. That takes time. There's a reason we invented our way out of copying books one by one, word by hand. So like that restaurant server from the last video who disgustingly licked my plate clean instead of getting me a new one, lick that plate and hand it right back, and lick that plate and hand it right back. You don't have to spend all those resources allocating and copying over an array, or putting that plate into the dishwasher and using all the water to clean it and storage space. Instead, you just work with the array or the plate that you already have. Oftentimes, you're trading off performance and efficiency for clarity of code. There are of course many ways to mitigate this. For example, in a function, if you know you're going to be modifying an array a lot, you can use a mutable array inside that function as long as you're not changing stuff on the outside. This sort of confines that mutability to just one function, which is a lot easier to track down, and it's a little bit encapsulated. Also, maybe some languages have some optimizations, like if you ask it to copy an array and add on an extra element, maybe under the hood it just uses the same data and keeps track of that somehow. I'm not really sure. And if you know, please let me know in the comments. Generally though, for most apps, this bottleneck is not a huge problem. It would likely only come up if you're dealing with huge data sets. So for me, I think it's easier to start with simpler code that's easier to understand and compose and maintain and refactor, and optimize if and when you need it. Usually this is more about concurrency than it is about the sizes of arrays. Okay, so terminology, dirty little secret number 1. I used a little sleight of hand for my terminology when talking about immutability. Immutability on its own defines data, not functions. It describes a data structure that inherently does not allow mutations. That is, the data structure ensures that when you interact with it, you're not allowed to change it in place, but instead, make copies with changes. This comes up a lot more in object-oriented programming, where objects are the primary focus of your code architecture. For example, you can define a person class, which is basically a blueprint describing how you can interact with any individual person in your program. Since a person class is in control of how you interact with that person, it can choose either strategy for how you are allowed to interact with it. Let's say, for example, we model a person to have a name and an age. And the class allows for increasing somebody's age by 1 on their birthday. If you choose to make the person class mutable, you might add a haveBirthday function, which internally increments the age of that person by 1. This function would mutate the person by incrementing their age state by 1. In order to make the person class immutable, your haveBirthday function would instead copy over that person's attributes into a new person object, increase that new person's age by 1, and return that. Now, when you call this immutable haveBirthday function on a particular person, that person is not modified. Instead, you get a new person with all the attributes copied from the previous one, except with an age increased by 1. Happy birthday! However, in functional programming, functions are the focus of your code architecture. Get it? Object-oriented, functional programming. You model your app more by thinking about the functions and what they're due, rather than the objects and the capabilities they have. So instead of going around making your objects immutable, like in that person class example, it's more about making sure that your functions choose not to do any mutation. So technically the word immutability doesn't actually describe functions, but a function that does not do any mutation is called pure. And obviously that's pretty related. For us in this series, we will follow the code and use pure functions to enforce immutability. I solemnly swear that our functions are up to no mutation. Okay, so I also use a little sleight of hand when talking about pass by value versus pass by reference. In JavaScript/TypeScript, everything is pass by value. I know, I'm a liar and I'm sorry, but all array and object variables are stored by reference, so just hold on. Here's what I mean. For primitive types, the explanation remains the same. They're passed by value, so any reassignment inside a function is not reflected outside that function. Check out this mutating add1 function. We accept an input called num, which is a number. And inside the function, we reassign num to equal num plus 1, basically adding 1 to that variable. Here, we can see that it doesn't modify our variable outside that function. We create a variable called num set to 1, pass it into our so-called mutating add1 function, and if this were a mutating function, we would expect to get back 2, but we don't. That's because the primitive type number is passed by value, so the function gets a copy of it. It does not have the ability to mutate that variable and have those changes reflected on the outside. Similarly, this function tries to append an Similarly here, this function tries to append an exclamation mark to the end of the string that we give it. And just like for numbers, strings are also passed by value, so our input hello is not changed outside of the function. But arrays are passed by reference, so we know that our familiar append function that does array.push will actually modify the input variable. And we can see this here. We give it an initial set of numbers, 0, 1, 2, pass that into the function, and then it is modified by getting an extra 1 tacked on to the end. Pause here if you want to see more. Here's a quick example of how an object is also passed in by reference and can be mutated from inside the function. So for primitive types, the only option we have is to return a new value. This add1 function does the same thing as before, but now it returns num at the end. And in the test, we pass in our same input, but now we have to assign that return value to a variable. And since both variables are numbers and they're primitives and they're passed by value, they both retain the values 1 and 2. Pause here again if you want, but here's the same change made to our string append function. And for arrays, we've made the same change to this append function as we did in the last episode. You can see how it takes intention for a function to choose not to modify its array or object input. That is, we have the ability to mutate our input, but we can choose to not mutate it and instead return a new array with the updates. Again, it's the responsibility of the functions to follow the code and not partake in any mutating behavior.
There's more what you call guidelines than actual rules.
Don't do it. And here's the example for an object that uses object destructuring to overwrite some properties and return a new object instead of modifying the object that was given to us. Pause here if you want to take a look for a little longer. Coming back to that terminology thing, again, JavaScript/TypeScript is always passed by value. It just so happens that arrays and objects are always stored by reference. So when we pass in an array to a function, we are passing it by value, it's just that the value is a reference to the array. Whatever. True pass by reference can happen in languages like C, where even primitive types can be modified from inside a function. But that's out of scope for this whole series since we're in TypeScript, and those are just details. For the most part, I think it's just a simpler mental model to think arrays and objects are passed by reference, and primitive types are passed by value. That rule of thumb guides you towards the same software design principles, and is an easier reminder that arrays and objects can be mutated. So it's good enough as a working principle. Okay, so also I didn't have time to touch upon equality by reference or equality by value. Long story short-ish, you have to be careful when you're comparing values in JavaScript. Since primitives are stored by value, when you compare them with triple equals, it does what you expect. But always use triple equals, never use double equals. Go check out something on the internet about that. But when you're comparing arrays and objects, you're comparing the references. So any two variables that point to the same place in memory will be equal, but it's entirely possible you have two different arrays stored in two different places in memory that so happen to have the same values, and if that's what you care about, then you have to actually go into the array and compare every single value one by one. So the out-of-the-box operator triple equals compares variables directly. For arrays and objects, that means comparing their references. In order to do more complex tests for equality, like checking the actual values, you have to write a function that will do that. There are many resources online about comparing arrays and objects for equality, so that's out of scope for this video. But what is cool is how functional programming will allow us to combine multiple equality equality testers to create more and more complex equality testers. That's gonna come a lot later, but I just wanted to mention this for now. Planting the seed. So that's it for this weird little short video in a new format. The sun's going down because it's December when I'm recording this, even though you're probably seeing this weeks or months or maybe years later. Please let me know what you think about the series so far, both in terms of pacing and in length. Have you been able to follow along? Did you have to pause? Are you okay with that? I want to find a balance between education and entertainment and make sure that the series is accessible enough for non-engineers to watch it. It's about finding that balance between going slow enough to explain things well, but going fast enough to make sure people are not bored.
Boopy doopy doop boop sex.
So let me know your level of background and experience, what you want to get out of this series, and I'll be able to tailor the content to you. Oh, and don't forget that feedback on my shirt. Me and this shirt, we'll catch you in the next one. Bye!